In this unit, we want to discuss a classical treatment, a very simplified classical treatment of the hydrogen atom. And what we want to do, the purpose of this is to introduce some features of the problem that we should really know about before we approach the problem using quantum mechanics. In particular, we want to talk about the nature of the forces and the potential energy in the problem of the hydrogen atom, and also we want to introduce the concept of angular momentum, which plays a very important role in quantum mechanics. So first, let's see, we will, and also one more thing, we want to talk about the very simplified quantum model for the hydrogen atom. This is the old quantum theory of the hydrogen atom due to Bohr. Now the Bohr model, while incorrect, does introduce the idea of energy levels, and it happens to give exactly the correct formula for the energy levels as the more properly treated quantum mechanical problem. So to start, we say basically the problem is one of two particles, an electron and a proton, attracted to each other via an electrical force. So just like the nuclei in the vibrating molecule, these two particles move about their common center of mass. As in that problem, we can treat the motion of two particles as really the motion of a single particle with a so-called reduced mass, mu, here, and with the same definition. And in this formula, m sub e is the mass of the electron, m sub n is the mass of the nucleus. However, because the electron mass is so much smaller than the mass of the nucleus, actually the nucleus in the hydrogen atom is a proton, which is between 1 and 2,000 times heavier than the electron. The reduced mass is almost equal to the mass of the electron. You can see this if Mn is much greater than Me, this formula then becomes Me, approximately equal to Mn, over, and then this denominator is approximately just equal to Mn because it's so much greater, and I can see that these cancel, and this is approximately equal to m sub e. In the formulas that I'm going to give, we can, to a pretty good approximation, regard the problem to be one of an electron moving in the vicinity of a fixed nucleus, which defines the origin of the coordinate system. And so in the formulas that we're going to derive, we're going to use the mass of the electron, and you just understand if we want these formulas to be much more precise, we would use the reduced mass instead. Now the potential energy for two charged particles is given by this formula. V of r is the product of the charges. Q1, Q2 are charges, and in standard SI units, these would be charges in coulombs. They can be positive or negative, and expressed in standard SI units, there is this denominator, this constant that's called epsilon naught, the electrical constant, and 4 pi epsilon naught appears in the denominator here. And so these can be positive or negative. V of r, if the two particles are the same sign, the product in the numerator is positive. If they're opposite sign, it's negative, reflecting an attraction. If they're the same sign, there's a repulsion. The denominator in here has r. R is the distance between them, and when we do the problem more fully in the quantum mechanical treatment, we will have spherical coordinates, and instead of x, y, and z, for the position of the particle, we will have r, theta, and phi, where theta and phi are the two angles. We're not going to deal too much with the angles here, but notice that the potential energy takes a particularly simple form when expressed in terms of r instead of x, y, and z. So what are the charges in this problem? Well, first of all, we have the charge of the electron, Q, we'll call it Q1, is equal to minus E. E is the charge of the electron, and if we're doing SI units, we can look up E. We find it's approximately equal to 1.6 times 10 to the minus 19th coulombs. Excuse me. Okay, there. Q minus E, 1.6, so it's negative. The charge of the nucleus, the charge of the proton, as you know, is plus E. I'm going to introduce one more thing. As long as we're doing the hydrogen atom, and we might as well kind of along with that do any atom. Along with it, do any so-called hydrogen-like atom. That is anything where we have one nucleus in the vicinity of one electron in the vicinity of any nucleus. So it doesn't cost us anything. We just have to carry along another variable called Z. Z is the atomic number, and so Q2, the charge of the nucleus, the other particle involved, is going to be plus ZE. Okay. Putting these into the equation for the potential energy, Q1 being minus E, Q2 being plus ZE. We wind up with this general formula for the potential energy of associated with an electron and a positive nucleus. So VR is minus ZE squared over 4 pi epsilon naught R, the distance between them. So what does this look like? I'll put up a graph showing the potential energy as a function of R. This graph shows that function specifically for the hydrogen atom, where Z equals 1, Z equals 1. And then some things to notice about it. Notice that within this model, notice that the potential energy is at all points negative. A potential energy of 0 up here represents 0. It approaches 0, and that represents the two particles being separated from each other. And at any distance less than infinity, the electron and the proton have negative potential energy. The potential energy approaches negative infinity as R approaches 0. And on my graph I have actual energies where I have R in nanometers and V, the potential energy, in electron volts. Now the force that exists between these two particles is, written in the force as a vector, is the gradient, the negative gradient of the potential energy. Now you can show, I will not do that here, but it should seem reasonable that the magnitude of the force, not its not its direction, but the magnitude of the force is, it's just like in a one-dimensional problem, is the negative derivative of v with respect to r. And if I do that, notice that so I'm taking the derivative of a constant over r, and I take the derivative and I get a constant over r squared instead of r. And so that's the magnitude of the force, and the direction of the force, as you probably know, is a vector, that force is a vector directed to the origin. On the plot, that force would be the force at a particular point right here, say at this distance r. It's the negative slope of this of the tangent to the potential energy curve, and is directed towards a smaller radius. So that represents the fact that the electron and the proton attract one another. Notice that the force is greater greater at shorter distances, and we have a smaller. We have at some other distance, say right here, we'll have a smaller force because the slope is the magnitude of the slope is correspondingly less. So that's the nature of the potential energy between the potential energy and the forces between an electron and a positively charged nucleus. I'm going to put in the next lecture. This will be the end of this lecture. In the next lecture, I will show. We'll discuss not the solutions to this problem in general, but the specific solutions of those of circular orbits of the electron around the proton or other positively charged nuclei.